can assert that the light that bounces from a mirror is being reflected. But what about that bouncing out of the wall or from a cloud? We need to discuss such wave behaviors before attempting to apply our knowledge of waves to real-life topics like echolocation and many others. This is class number 10. Before we begin explaining the world we're in and understanding some of today's familiar applications, we must abandon some of the idealizations we made in class number 9 and come nearer to reality. Starting with the simplest of the 5 F's, reflection. The one we introduced then was the specular type, that in which the plane wave was reflected in the same angle it was incident. However, for it to happen, the surface must be a smooth one. A rough surface will produce a diffused or scattered reflection. But how smooth the surface must be for producing a specular reflection? Smooth, say, at an atomic level, as the surface is exposed by the cleavage of a crystal, like a diamond face? Nah, not that smooth. Wavefronts describe the phenomena more accurately. Consider the reflective wave in normal incidence. Specular reflection will happen whenever the wavelength is much larger than the grain of the irregularities. A wave that large cannot resolve details much smaller than its wavelength. If the grain becomes comparable to the wavelength, then the reflection will be a diffuse one. Here's an everyday example. Headlight restoration by polishing. First, for getting rid of scratches, the surface is sanded with 500 grit paper, which leaves a grain of about 25 micrometers. Reflection is almost perfectly diffuse. Next, the surface is sanded with 3000 grit paper. This reduces the grain to 6 micrometers. Some specularity is starting to show. Finally, the surface is polished with a compound that leaves the grain smaller than 0.05 micrometers, 10 times smaller than the wavelength of visible light. And that makes all reflection specular. Notice the perfect definition of the ceiling lamp images. Theater walls and ceilings are not specular for light, but unfortunately they are for sound. And this causes echoes and reverberation, which are undesirable features in theaters. For humans, the shortest hearable wavelength is of 17 millimeters, and that is more than 10,000 times the longest wavelength of visible light. Modern techniques have been developed to avoid sound specularity, like convex ceilings and panels hidden behind sound-transparent concave walls, as well as some other ingenious tricks for extending coverage. But this gets weirder. A parabolic reflector for a flashlight must be as smooth as a mirror. Yet one for a UHF antenna may even have holes to make it lighter and stand better against the wind. The wavelength that the shown antenna radiates is about 1 meter. There are 870 holes in that reflector. Don't you wonder why waves are not escaping through those holes? It turns out that the part of the power of a plane wave that manages to get through a hole of radius r much smaller than the wavelength goes with the fourth power of the ratio of the perimeter of the hole over the wavelength. Like that.
That can probably be derived from Huygens' principle and Fresnel's diffraction equations.
I must admit yours was a good guess. Those were brilliant minds of the 17th and 1800s. But that equation there had to wait for Nobel laureate Hans Bethe in 1944, while working in the Manhattan Project.
The bomb.
Yes, the bomb. Okay, let's get on with this. From the picture, we can estimate the hole diameter as having 1 centimeter, and the wavelength was 100. If we assume that when the wavelength equals the perimeter, all the power arriving to the hole manages to get through, which of course is much less. Evaluating the ratio for the actual wavelength, we get 10 to minus 6. Even having 870 holes, the power leaking through is less than 1/1000th of the power hitting their area. What about the opposite problem? A plane wave hitting not a hole much smaller than its wavelength, but a similarly sized object. This effect is called scattering. It was Lord Rayleigh that from 1871 to 1899 studied this problem. His motivation was that of explaining the blue of the sky and the red of the dawn dusk. So already knowing that light was an electromagnetic wave, he figured that the electric fields in the light waves induced electric dipoles in air molecules, and that these oscillating dipoles were the ones producing the scattered radiation. Following that line of thought, he went on to predict the angular radiation patterns, quantize the set polarization according to the type and size of possible atmospheric obstacles, but here's the icing on the cake. The radiated power from a small dipole goes with the fourth power of the frequency. Therefore, scattering from polarized air molecules should have the very same frequency dependence. Since the frequency of the bluish light is about 1.5 of the reddish, it will be scattered some 5 times more. And
heavenly shades of night are falling, it's twilight time.
in a sunset, the white light coming from the horizon must travel many miles through the air, and most of the blue light will be lost to scattering, allowing the red to prevail. The sky above our heads, on the other hand, is scattering the blue, and that's the color we see.
Then why are the clouds white and not blue?
Intelligent question. Clouds are made of small water droplets floating in the air, too small to drop as rain, but still much larger than visible light wavelength. So all the components of white light are specularly reflected, like from small spherical mirrors, and that's why clouds are white. So when obstacles are much smaller than the wavelength, the Rayleigh scattering happens, and the radiated power goes with F to the fourth power. If the opposite, then the scattering will be due to specular reflections and become independent of frequency.
What about the in-between? Hey, intelligent questions are my thing.
What's so intelligent about asking for something that obviously I was about to introduce, which is the scattering from objects comparable in size to the wavelength? It is called the Mie scattering after Gustav Mie. As the wavelength nears the perimeter of the obstacle, it will scatter light waves as if it was larger. Whenever multiples of the wavelength come near the perimeter, resonances are observed, which are less pronounced as n increases.
We may not be learning much about sound, but at least we're being enlightened.
Amazing how something that wrong can sound funny. Though scattering was studied for explaining some light behaviors, it is a wave thing, and so works for sound as well. For instance, backscattering is a better description for what mostly happens in echolocation and medical ultrasound, and not reflection. That's why this class is still about the physics of sound.
Silly clown.
We're ready now to apply our sound waves knowledge. How about the SONAR, which is an acronym for Sound Navigation and Ranging? The principle is easy. A beam of short sound pulses is sent out, the target backscatters them, and the distance can be determined from the delay. It was developed for detecting subs. The first unit came out as early as 1918. It took 6 decades and a revolution in electronics for the fishermen to inherit the sonar from the military. Today, it is a widespread technology. Every fishing boat out there has got one. But as they say, the devil comes in the details. For instance, how do you send a beam of sound into water? Water is tougher to compress than air, so a speaker from the water must deliver great pressure but little displacement. In the sonar terminology, these are called transducers, and they can be either piezoelectric or magnetostrictive. Some substances in crystal form exhibit piezoelectricity. When stress is applied to such crystal, an electrical potential generates between its opposing surfaces. Receiving transducers take advantage of this effect. Conversely, if a voltage is applied, then a strain is observed, and this is how it can also work as a speaker. Piezoelectricity was first observed and explained by the Curie brothers in the 1880s. Magnetostriction was first reported back in 1842 by the great Jean Prescott-Joule, the very same that proposed the conservation of energy. Ferromagnetic alloys exhibit magnetostriction. This effect is the change in some dimension when magnetic field is applied, so that is good for transmitting sound into liquids and solids. Same as piezoelectricity, the inverse effect also happens. A strain produces a magnetic polarization, and that can be used for receiving.
Which one's better?
Well, it has gone back and forth. Originally, piezoelectricity in quartz was used for the first transducers. But these were fragile and unreliable, so magnetostriction took over. Time went by and advanced piezoelectric ceramics were developed. That brought piezo transducers back into business, and these are prevalent today. No matter which type, a transducer vibrating through a hole in the hull of a ship exhibits the familiar diffraction pattern of the single slit. And that explains why the larger the wavelength, the wider the beam must be. Same goes for receiving transducers. Sensitivity share the same patterns of transmitting ones. It happens that as the frequency increases, not only the beams can be made narrower, but more power is backscattered from smaller targets, rendering a higher resolution.
Then the higher the frequency, the better, right?
Not so fast. As frequency increases, the absorption due to water viscosity increases as well, damping the echoes from far targets. That results in a shorter ranging capacity. What about distance determination? What should be the interval T sub I between pulses? Say we're fishing on a depth D equal 10 meters of water. The echo from the seabed would take a time Td equal 13 milliseconds. Then the pulse interval should be greater than 30 milliseconds. Too easy, right? The interval between pulses must be longer than twice the time it takes the sound to go from the transducer to the seabed. But as pressure builds and temperature lowers with depth, sound slows down and speeds up again. This not only makes time non-linear with the depth, but sound no longer propagates in a straight line due to refraction. At incident angles large enough, even total reflection happens.
Like the mirage effect in hot air.
Ha, that was a great analogy, Sebastian. What about distance resolution? If two near targets cannot be individualized, the resolution is insufficient. With pulses that wide, the echo from those two targets cannot be resolved. Obviously, the pulse width T sub PW must be shorter. With shorter pulses, the two targets are resolved.
The narrower the pulse, the better, right?
Well, the narrower the pulse, the higher the resolution, but better? Let's focus now on the receiver of the sonar. What limits the capacity for detecting echoes?
Well, there must be a limit to the receiver's sensitivity.
There's no such limit. What limits the detection of any signal is always noise. No matter how faint the signal, if the noise from the environment is small enough, it can always be detected. There are many sources of noise in the sea. Some are natural, like waves or bubbles, underwater earthquakes, or biological, from sea creature calls and snapping shrimp. Sources from human origin are ships, drilling, and nearby sonars. The noise power increases with the receiver bandwidth.
Then, the narrower the band, the better, right?
The narrower the band, the less noise. But again, better? The narrower the band of the receiver, the slower its response time. Remember that product of tau by delta omega being greater than 2? The response time by the bandwidth is greater than a constant. This means trouble with short pulses. Short echoes coming from small and faraway targets may get buried in noise. Pulse and bandwidth become a trade-off between resolution and sensitivity. It's a compromise.
I've heard that bats have kind of a sonar, yet they manage to spot a mosquito as well as huge distance objects in the dark. Find a way in caves, all while flying at full speed. They don't seem to be compromising much, right?
Bats have been using echolocation way before humans even existed. Evolution had sophisticated the sonar in ways beyond what we have explained here. It has not been until quite recent, after great effort and a lot of technology, that humans had figured out how bats do it. Bats emit many types of calls, but when out for prey, they use low-frequency chirps at long intervals to recon their environment. While doing this, the bat may pick up some faint Rayleigh-type backscattering from a potential meal flying nearby. The bat then sends an intense and very special high-frequency chirp in the direction of the scattered sound. Its echo will bring information on the size and precise location of the prey. Next, one less insect in the world.
What's so special about those high-frequency chirps of the bats?
One feature that makes those chirps very special is that of being frequency modulated. It depends on the species. For instance, a high-frequency chirp from an Indiana bat shows the time dependence in the chart. It cannot be heard by humans, but if we slow it down 10 times, it would sound like this. The chirp changes frequency during this 7 millisecond call at a rate of approximately 7 kHz per millisecond. Say that the potential meal is a moth, the size of which is 1 centimeter. A time of 0.06 milliseconds is what it takes for the waves bouncing from the head to reach the back of the moth. But by then, the frequency being scattered there is already approximately 0.4 kilohertz lower.
And they beat at 400 hertz.
The higher the beat frequency, the larger the meal.
Sonar engineers could learn a thing or two from those bats.
Actually, they have. As soon as enough computing power became available, some features of bat echolocation were implemented. Inspired by bat chirps, sonar designers came up with one that uses longer but frequency modulated pulses. And guess how this new technology is called? Chirp. Great acronym. After digital processing the scattered sound signal, resolution improves with the same bandwidth. Check that out. As better instruments develop, humans are learning more every day from bats and these are the masters of echolocation.
And this brings us to...
Well, it's that time. Time for the quiz. Here the answers will follow the question or problem, but hit pause and try answering it first. Say if it's true or false. Rough surfaces, no matter how small the grain, always produce diffuse reflection. Now hit pause and try to come up with an answer of your own. When the grain is much larger than the wavelength, rays can tell the story. Incident angle equals that of reflection on every grain of the surface. However, when the grain is much smaller than the wavelength, wave fronts reveal better what goes on. Those waves don't see a grain that small, and the reflection becomes specular. All surfaces in a stealth fighter are specular to radar. A flashlight won't reveal a mirror in the dark unless it's perfectly facing it. Though you can see stealth fighter for the surface not being mirror polished. To much larger radar waves, it is perfectly specular. The white light that manages to go through an opaque surfaces with holes of perimeters 10 times smaller than its wavelength looks bluish. According to Nobel laureate Hans Bethe, the power that manages to clear a hole much smaller than the wavelength goes in proportion to the fourth power of its perimeter to wavelength ratio. That there. Being blue-violet wavelength 1.5 smaller than the reddish, that to the fourth power is then 5 times stronger in the light behind the surface. So yes, it's bluish. The light reflected by the surface above, the one with the holes, is reddish. Again, using the Bethe equation, that one there, the power that manages to clear a hole with perimeter 10 times smaller than the wavelength is less than 10 to minus 4. So, at least 0.9999 of the power of the light, even the blue-violet, is reflected. Hence, no, it's not reddish, but still white. Stereo speakers with metal cones are typical in sonar fishing applications. Normal stereo speakers are good for creating sound waves in low impedance medium like air, where acoustic pressures are low and displacements large. A fish is a water creature, and water is a high impedance medium, meaning high acoustic pressure and small displacements. Piezoelectric and magnetostriction effects are the ones used to send audio signals into liquids and solids. Short sonar ping pulses render high resolution in distance determination. Long ping rebounds may overlap if targets are nearer than half the pulse width by the speed of sound. The shorter the pulse, the higher the resolution. The statement is correct. Sound in seawater always propagate in straight lines, same as in the air. That would be true if density and temperature were constant in the region, but refraction will happen if not. In the sea, as water cools with depth, and density increases even at greater depth, propagation of sound may not follow a straight line. Bats are blind, but feature a primitive version of a sonar to hunt and navigate in the dark. Bats are neither blind nor their sonar is primitive, but more sophisticated than the best models in the market. Problem number 1. The image is that of a fishing sonar. The transducer diameter is D equal 50 millimeters. Estimate the angle of the main lobe at 200 kilohertz. There's a hint. Single slit diffraction pattern, anyone? Using the single slit diffraction pattern, the main lobe angle will be twice of theta, when diameter d by the sine of theta over lambda equals 1, or when theta equals the arc sine of lambda over d. Being lambda, that is 1500 meters per second, over 200,000 equal to 7.5 millimeters, then alpha is twice the arc sine of 7.5 over 50, which is approximately equal to 20 degrees. And that is the answer to the problem. However, manufacturers specify the main angle not for zero intensity as we just did, but for half the intensity, and this comes to about 10 degrees. But maybe to avoid claims and lawyers, the spec is advertised at 12 degrees. Problem number 2. The body of a fish is mostly water, except for the air bladder, and this is the only part of the fish that can scatter a sound beam from a sonar. This is a fish when seen from the top, but what the sonar sees and senses is just the bladder. Say there's a school of sardines with the shown sizes. Estimate the intensity ratio in dBs of the return signals from 50 and 20 kilohertz pings. The wavelength of 50 and 20 kilohertz in water are 30 millimeters and 75 millimeters respectively. Both wavelengths can be considered much larger than the size of the obstacle, so it's a Rayleigh type scattering, in which case the scattered sound intensity goes with the frequency to the fourth power. The intensity ratio is 10 by the log of 50 over 20 to the fourth, which comes to 16 dB, the requested figure. Problem number 3. Can you explain why is this happening? A speaker out of the subwoofer box cannot play bass sounds. High-pitched sounds with frequencies above 1 kHz have wavelength comparable to the size of the speaker. I mean less than 33 centimeters. Little diffraction is created and the sound is directed to the front and the back directions. And so the back wave doesn't interfere with the front one, which is the one we hear. Bass sounds with frequency below 100 Hz have wavelengths much larger, greater than 3.4 meters, than the size of any speaker. When inside the box, the back wave is absorbed. When out of it, this back wave diffracts and interferes destructively with the wave from the front, almost cancelling it. And that's why the bass disappears. The question has been answered. Here's problem number 4, the last one. When you apply a sinusoidal wave of 20 Hz to a big speaker, you see a displacement of about 1 centimeter. Then, using the same power but at 200 Hz, the displacement is much less. Why? And how much less? Wave power goes with the square of the speed involved in the acoustic motion, and the speed is proportional to the frequency and the displacement. Being the power the same, the product of the displacement by the frequency must remain constant. So, if the frequency went up by 10, the displacement must come down by 10 as well. The displacement must then be 1 millimeter, which is the answer to the question. Music is already revealing the end of class number 10. But there are interesting topics still pending. How about ultrasound imaging, sound in periodic structures, seismic wave, Doppler effect, or the supersonic boom? Subscribe to the channel.